Good morning. In continuation of previous video, as I explained in the previous video, what is p-n junction diode? How do we form the p-n junction diodes? So in this video, I am going to explain the operation of p-n junction diode under three conditions. So that means operation of p-n junction is studied under three different cases. One is under no bias, forward bias, and reverse bias. So we'll see one by one. So this is the question appeared in the exam. Yeah. Under unbiased. Unbiased means we are not applying any external bias voltage. Bias means we apply external voltage. So unbiased means, so this is an unbiased condition. Unbiased condition. So before they diffuse, electrically neutral. When they start diffusing, it forms a depletion region. So depletion width during the unbiased condition. This is N type and this is P type. So positive charge on the N side repel the holes cross from P to N side. See this one. So positive charge repels the holes, and similarly negative charge on the P side repels the free electrons to move from N type to P type. So that means barrier is set up. Barrier is set up against the further movement of charge carriers, called potential barrier or junction barrier. And this potential barrier is 0.7 volt for silicon and 0.3 volt for germanium. So that means we have two types of the most popular semiconductor metals is germanium and silicon. So potential barrier against the flow of electrons from N side is negative. I mean, this is due to charges on the electrons is negative. Similarly, potential barrier against the flow of holes from P side to P side is positive. This one, okay, due to charges on the hole is positive. This is unbiased. So now let's see forward biased. So this is unbiased condition. And here the diode is said to be forward biased when positive terminal of battery is connected to P type and negative uh, terminal is connected to N type. Okay, that means, so when you connect the potential, depletion region get reduced. See, this is unbiased condition. When you connect the positive terminal to P type and negative terminal to N type, it is get reduced. It is get reduced. This is the depletion region when forward bias voltage increases. Okay, this is the positive ion and negative ion. So that means this is the circuit diagram. This is the circuit diagram. That means forces electrons to move from N side to P side due to negative polarity of the supply. This one, negative polarity of the supply, by gaining sufficient energy and reduces the potential barrier. But some electrons are entered into depletion region and combined it becomes the positive ion. Similarly, by gaining sufficient energy from the positive source, P type holes from the P types are moving towards the N type, but still some are recombined. Okay, so that is why, so we have a narrow depletion region compared to the unbiased. Okay, as we further increase the applied voltage, see this is the applied voltage. Further, if you increase the applied voltage from 0, potential barrier get progressively decreases. I mean, this potential depletion region progressively decreases and disappear. Then electrons or holes move across the junction freely. Okay, so holes travel from left to right and electrons travel from right to left. Hence, resulting current is sum of electrons and holes. That means current in the forward bias is equal to current due to N type IN and current due to P type IP. IF is equal to IN plus IP. Now we'll see a reverse biased. So the diode is said to be, so this is the one under unbiased condition. So that diode is said to be reverse biased. So when you connect positive terminal to N type and negative terminal to P type. Okay. So depletion region becomes increases because see here the unbiased condition, This positive voltage is, this attracts the electrons. I mean, electrons are moving away from the junction. Similarly, this is negative charge, no? So this negative charge attracts the holes, positively charged holes. So holes are moving away from the junction, away from the junction. That is why depletion region get increased. Depletion region get increased. And this is the corresponding circuit diagram. So holes from P side are attracted to negative terminal of the battery. Okay, the holes are attracted here. Similarly, electrons from N side are attracted to positive terminal of the battery. I mean, this charge attracts the electrons. That means both majority charge carriers move away from the junction. As a result of depletion layer gets widened. Okay. So wider the depletion region, greater the difference in potential across the junction. I mean, the potential barrier increases. Potential barrier increases. Okay. So when you increase the reverse voltage, VR is called as a reverse voltage, the barrier potential also increases. I mean, depletion region also increases. When reverse voltage is equal to potential barrier, barrier stops growing. I mean, it's keep on increasing the barrier potential. That when the barrier potential is equal to applied voltage, it starts going. So when this happens, majority charge carriers in the P type starts moving away from the junction, creating an electric field. Electric field. But some minority charge carriers here, some minority charge carriers are there, electrons here, holes are there, no? They recombine with the majority charge carriers. So very small magnitude of current IO, that is, starts flowing in the electric field, electric circuit, in the direction opposite to conventional current. Hence it is called reverse saturation current. So that magnitude of reverse saturation current depends only on the junction temperature. It is not depends on the applied voltage VR. And for silicon, that reverse saturation current is in the order of 1 microamps, and for germanium it may exceed 10 microamps. So this is about reverse biased PN junction. Remember, the reverse biased PN junction, a very small magnitude of reverse saturation current, that is due to minority charge carriers. Now we'll see characteristics of PN junction. That means uh, plot of voltage versus current. Okay, VA characteristics is a plot of applied voltage across the PN junction and the current flowing through the PN junction. So again we have forward characteristics and reverse characteristics. So first we'll see forward characteristics. So this is a simple circuit. This is a simple circuit. Here we have one diode and resistor. This we call as a current limiting resistor. So to this diode, positive terminal is connected to anode and negative terminal is connected to cathode. So it becomes forward bias. Hence there is a current flow in this direction. So IF means current during the forward bias is equal to I max, maximum current. This is the applied voltage. Okay. So from the figure we know positive terminal supply is connected to P type and negative terminal is connected to N type. If the supply voltage is very less compared to cut-in voltage, as you know, cut-in voltage is 0.7 for silicon and 0.3 for germanium. So where this is the characteristic. Yeah. See, barrier potential or cut-in blocks the movement of majority charge carriers and its forward current to the diode is very low. I mean, this is the one. See, very low current, very low current. Okay, until it crosses cut-in voltage, that is 0.7 volt for silicon. Okay, so if the voltage V is greater than cut-in voltage, then the barrier potential reduces and IF increases almost linearly. Almost linearly. This is forward bias. So this is clear, no? So now we'll just express the relationship between voltage and current mathematically. It is expressed as IF is equal to I naught into e to the power V by eta Vt minus 1 amperes. IF is a forward current IF is a forward air current, IO is the reverse saturation current, V is the applied voltage, Vt is the thermal voltage. Thermal voltage that is equal to Kt by Q. So where K is a Boltzmann constant, Q is a charge of an electron. As you know, this is a constant. Charge of an electron is 1.6 into 10 to the minus 19 coulomb, and Boltzmann constant is 1.38 into 10 to the minus 23 joules per Kelvin. Okay. So as you solve this value, you will get 11,600. This is Q by K value. So K by Q value becomes 1 divided by 11,600. So Vt is equal to T by 11,600. Okay, as I said, T is equal to temperature, absolute temperature in degree Kelvin. At room temperature, that is 27 degree Kelvin, is equal to 273 plus temperature in Celsius. So 273 plus 27, 300 Kelvin. So if we substitute T value, Vt becomes 26 millivolt. Okay. And eta is a constant. Eta is a constant. It depends on physical construction and operation of the operating condition. And it is 2 for silicon and 1 for germanium. It is about forward characteristics of PN junction diode. So in the next video, I'm going to explain the reverse characteristics.